come up what you think might be a good number. Okay, well. All right, well. Okay. What do you guys think? All right, so we're at something around 9.35 centimeters, okay? All right, and you know, if you said 9.36 or something like that, that's also fine, okay? So the idea it being that we are certain about 9.3, and then the last digit is the one we are uncertain about, okay? A little bit uncertain, okay? The last digit. All right. So here we get a good amount of well, I'll talk about this in a moment here, okay? But that's the idea behind using a ruler and trying to be as precise as possible. Now, some people, so I think most will say if you have this, you should say 9.35 or 9.36, okay? But some places will say do either 9.3 or 9.4, okay? And they don't want you to kind of interpolate something in between, okay? So, but I think, so most science textbooks will say 9.35, 9.36, just use your best judgment for that last decimal, okay? But then other people and might say, don't do that, just choose either 9.3 or 9.4, okay? And that's not wrong. Those are also fine to say, just you are kind of purposely limiting your own amount of precision in that regard, okay? So I'll say most textbooks recommend guessing or estimating the last digit. Okay. Some people say to report either 9.3 centimeters or 9.4 centimeters and not to what we might call it interpolate. No, that's not interpolating because we can see the line ending up certainly between 9.3 and 9.4. And at this point, I would say with a situation like this, it's really a judgment call on the person making the measurement of whether it's 9.3 or 9.4. Okay. And if you use a digital scale, that's essentially what it's doing. That last digit that the digital scale reports is usually the scale making a choice about the thing, using as accurate as the scale is able to be. Okay. So that's taking measurements with a ruler, and of course, if anytime you use a ruler, you want to make sure your left edge is lined up, and if it's not, you can't expect it to be accurate. Okay. Have you guys seen graduated cylinders or burettes? Okay. And did they teach you about making readings off of these? Okay. And so you have to read what they call the bottom of the meniscus, right? Are you able to see this this thing? Okay, so this says 13, and then you got little tick marks here. And so based on, and you know, you're supposed to go right at eye level. You can't take a measurement looking down, or you can't take a measurement looking up. You have to be at the eye level of the meniscus, and do your best for the measurement here. Okay. So this is all zoomed in. I don't know. Do I need to zoom in further, or are we okay? A little bit more. How do I do this? Okay. So the big line is 13 milliliters, and this would be 14. Or I think it's milliliters. Okay, so just your best guess. What do you think? So 13.1, 0.2, 0.3, 0.4, and then this is 13.5. So something between 13.4 and 13.5, and the last one you got to guess. And I think I said 13.45 or 13.46, something around there. Okay, 13.46. Does that feel reasonable? Okay, let's try again here. Okay, so I would say, you know, more than 14.0 but less than 14.1, and I don't know, 14.02, 03, 04 even, you know, it's going to be different depending on who you ask, because the last one is estimated. So 14.04. Yeah. All right, last one of these. This is 21. So 21, and then this down here is 22, so 21.20. Okay. Whoops. 21.20. This is okay? All right. Okay with you guys? Okay. All right. So, we will, oops. Okay, so when you get a measurement like 21.20 milliliters, or you know, something like 7.04 centimeters, okay, we can turn this into we should turn this into the actual liters, or no, actually, so it depends whether we're going to do some multiplication or some addition, but we should turn this into scientific notation, okay? And so we'll have 120 times 10 to the what liters? What do we do? Okay, so maybe we have to do a transition step to make sure we get the correct correct answer here.
We're doing liter. Oh, I'm sleepy, man.
Huh? You're still waking up here? I'm thinking negative. Wait, now you guys have confused me. It's in liters, so I think it's -2. Oh, yeah, see now I'm all confused. Okay, I'm pretty sure it's -2, but let's go. Okay, so we have. Oops. So we're gonna turn this into liters. So we have 21.20 milliliters. Okay, so if I go to liters, okay, I would have to go, a milliliter is 10 to the minus 3 liters, right? So 1 milliliter is equal to 10 to the minus 3 liters. So I would move this over three spots to the left. 1, 2, 3. So I would have 0.02120 liters. Okay? But then to turn it into scientific notation, I have to move this 2 spots over here. So my final answer is 2.120 times 10 to the minus 2 liters. I'm sorry?
Convert first.
Yeah. Okay, so then let's try out 7.04 centimeters, turn it into scientific notation with, something in meters. Well, yeah. So you move it over 2 spots to the right, and then you move it back 2 spots right. So you have 7.04 times 10 to the minus 2 meters. So we have, all right, so how do we, so a lot of times, so you may or may not be making measurements yourself, but a lot of times you'll see measurements reported, and maybe you have to do some calculations based off of reported measurements, okay? So we'll talk about how we should count how many digits are significant. Okay. And the rule is, so number one, maybe the easiest rule is any digit that is not 0 is significant. So basically 1 through 9, any of those are significant. Significant, the digits that come into question are the zeros. Okay, is a 0 significant or not significant? Okay, so any digit that is not 0 is significant. and also any zero that appears between significant digits is also significant. So if you have 2.1203, how many significant digits do we have? We have a total of 5 because the 2 also counts. So we have 1, 2, 3, 4, 5. We have 5 significant digits. Okay, and so now we want to ask, are the leading digits or the trailing digits significant? Okay, leading zeros and trailing zeros may or may not be significant. These are leading zeros and trailing zeros may or may not be significant. So generally, so if you have a 0 decimal with a bunch of zeros over here, these zeros are not significant.
Why wouldn't they be? They're placeholders.
Yeah, if they're just placeholders, they are not significant as part of the measurement. Okay. Let's see. Yeah, so the leading zeros, if they're just placeholders, okay, so leading zeros that are just placeholders are not significant. So this number here has 3 significant digits. Is that okay? But then trailing zeros after the decimal are significant. I know, it's all, the rules are, they feel crazy when you first learn them. But then with practice, you'll get used to it. So trailing zeros after a decimal are significant.
Seems reversed. Doesn't it seem kind of backwards?
I'll explain all of this, okay? So this number, 0.004500, how many significant digits are here? 4, okay? and it's this 4, this 5, this 0, and this 0 are significant. These are significant. Yeah. So 4 digits. And these are not significant. And I'll move this up. I don't know how much I can move up. So the 4 and the 5 are automatically significant because they're not 0. And then the zeros that come after, the trailing zeros, because they're after the decimal, are significant. Yes?
So every, so let's say instead of 2 zeros after 45, we say it's like 10.
10 zeros after 45.
Or, yeah, after the 45. Does that mean there would be like 12 significant figures?
Yes. If there's 10 zeros coming after the 45, that means there's 12 significant figures. Yes. Yes, question.
If the first 0 were a 1 with the 2 zeros in between, significant.
Yes. Yeah, if the first number, okay, so this is a good point. If we had 1.004500, now we have 7 significant digits. All digits here are significant, okay? All are significant. 7 significant digits. It feels weird and it feels uncomfortable, okay? We're not accustomed to using significant digits, okay? But remember, significant digits play a role when it comes to measurements, okay? If I count the students in this classroom, okay, or just this front row, I've got 4 students, okay? I wouldn't say I have 1 significant digit. That's just the number 4. And there's no significance attached to that because it's a count. It's not a measurement. I'm not measuring something. So it's not 1 significant digit. It's just the number 4. And that has its own rule also, I guess, just to make sure people understand the difference between measurements and something significant, okay? So trailing zeros after the decimal are significant. Okay, and this is the last rule. This is the worst rule of them all because it leaves the room for ambiguity. All right. So if you have a measurement, okay, so again, significant digits applies when we're talking about measurements, okay? A trailing zero before the decimal place are ambiguous. Okay? So if you see the number 200 as a measurement, okay? So, let's say somebody reports 200 meters. Okay? As a measurement, we are not sure. If it's reported like this, it is ambiguous, okay? Okay, some might say you have only 1 significant digit, which is the 2, and these zeros don't count. And others might say all 3 count. And so you have 3 significant digits. It's unclear here, okay? So, may have only 1 significant digit, the 2.
So is it just the last 0 before the decimal place is
May-
ambiguous, or is it all zeros in a row before the decimal place, which are ambiguous?
Okay, so let's talk, or we may have 3 significant digits. Yeah, I can't spell.
In those cases, there's no right or wrong answer.
I guess it depends who you talk to. So it is generally, it would be bad practice to report a measurement like this where it's ambiguous, okay? Now, if you're reading a report and it's reported like this, you don't have an option, right? But if you are in a position to report a number, you should not report it like this, okay?
What do you do? 200.1?
Yeah, so what you should do is, if you want to signal or say that you have 3 significant digits, that this last one is 0, you should report, you should write 200 point meters, okay? And if you put the decimal there, this tells people I have 3 significant digits, okay? This makes it clear that the last digit is significant, that the zeros are significant. Okay. Or you could put it into scientific notation, which would also make it clear how many significant digits you have, because you could, in scientific notation, you'd write 2.00 times 10 to the 2 meters. And here we would see, oh, we have 3 significant digits. But if somebody says 2 times 10 to the 2 meters, then you see, oh, I only have 1 significant digit. You know, so when you see something like this, it's unclear, okay? And so there's actually a story. The tallest mountain in the world is what? Mount Everest, right? And anybody know how tall it is? I think it's 23,000 feet, but let me just check. Height of Mount Everest. Sure. Valley guest 91401. Nope, I messed something up. Wait. Oh, now I'm locked out forever.
It's 29,000 and 29 feet. 8,148 meters.
What did he say? 29,000. 29,029 feet? Okay, so I think the story was, and I think it has actually gotten taller in the last few decades or something.
It went down.
Or it went down?
Yeah.
And down?
Earthquake brought it down on that.
Earthquake brought it down just now. But okay, so I think the story was when they first reported how tall it was, 29,000. The guy reported 29,003 feet. Okay, but the truth was, is when he took the measurements, all of the measurements were pointing to Mount Everest being 29,000 feet exactly. Okay, but he didn't want to report that because he thought if he reported that, people would just say, that's not very precise. I could have guessed it to the nearest 1,000 feet anyway, okay? Or something like that. And he wanted to tell the world, I worked really hard and I got a very accurate measurement, and so he just fudged the last number and he said it's 29,003 feet, okay? Because if because this looks like it could be an estimate, right? But when you say 29,003 feet, now it's like, ooh, That's very precise, okay?
It's like a lie.
So, but it was a small lie. But he wanted to kind of prove that he'd put in all of this effort to get as precise of a measurement, but he thought it would be a little sad if the most precise measurement was 29,000, okay? Because, and we're not thinking significant digits, but we recognize this seems a lot more precise than this, okay? Okay, so precision. So this seems more precise. More precise, so, and that kind of implies the underlying, how many significant digits do we have here? So this number has 5 significant digits. And this is ambiguous. Depending on who you ask, they might say you only have 2, or they might say 5. Now, he wanted to report that you had 5 significant digits, so he kind of fudged that last number there. You say, well, if I'm off by a few feet, no biggie. So, when you report numbers, this is ambiguous in how many digits are significant. When you put the decimal there, now it becomes clear that you have 3 significant digits, or if you put 2.00 times 10 to the 2, you have 3 significant digits, and this says you only have 1 significant digit. All right, how are we feeling? Good? Okay, so let's do some practice here, and I'm going to just put some numbers down. Don't shout out your answers, but we'll ask how many digits are significant. All right, do we have our answers? Okay, so how many significant digits do we have here? 5. All the digits are significant. What about here? 2, just the 1 and the 2. Over here? 5. Starting here, these are the significant ones. Here, I'll underline the significant digits. Over here? 3, and over here? 1. That's the only one. Okay. Okay. Are we all right with significant digits then? Okay.
I'm not.
You're not? Okay.
It's just a definition, right?
It's just the definition in terms of, and again, assuming these are all measurements, okay? The under, assuming. These are all measurements. So some kind of measuring device, right? Either a ruler, a scale, or whatever it is that you're using to make a measurement. Okay, if you're counting something, it doesn't count. If I'm trying to think what other situations where you don't have significant digits, and it might appear that you do. So anything that's coming from a measurement will have significant digits in play. Okay.
What about if it's like this like 3 monkeys?
Yeah. So if it's a count, if you're counting something, it's significant digits don't come into play. All right. So you don't use that in your figuring of significant digits. Okay, and this all comes into the worst part of significant digits. So we have the definition of significant digits and how to count them, and then we're going to learn the rules about significant digit math or significant digit arithmetic. And this is like the worst part of significant digits. And I apologize. It's not fun because all the rules you've learned about math and arithmetic kind of go out the window when you do significant digit arithmetic. Okay, and but it's the idea of you buy the bag of potatoes. You can't give an answer that's more precise than to the nearest pound, even if you're throwing on little. Even if you get accurate measurements for the carrots and these other things, if you've got this bag of potatoes with all of this uncertainty, you can't have anything, you can't give an answer more precise than what you have there. Okay? And the rules are very different when you're doing multiplication and division versus addition and subtraction. So we'll save this. Okay, so we got to go into significant digit arithmetic. And these are the no fun rules. Okay, so for multiplication, this is multiplication and division. Your final answer cannot have more significant digits than the measurement with the fewest significant digits. Okay, and then for addition and subtraction, and let me highlight measurement there, okay, or underline. Addition and subtraction, your final answer cannot have, what is it, more decimal places, not significant digits, but have more decimal places than the measurement. The fewest decimal places, okay? So these are the overarching rules that will apply to all of our future calculations. Okay, do we have all that written down? Okay. Oh, not yet. Okay, I'll go back. Oops. There you are. All right. Can I flip to the next slide or next page? Okay, so again, all of this, before we get into it, so the significant digit and decimal place stuff, significant digit rules apply generally only to measurements, okay? So apply to measurements only. Okay, they do not apply to, counts. So if you count something, like 3 monkeys, it doesn't apply. So you don't take into, if you counted 3 monkeys or whatever, you don't take that into your digit calculation and say I only have one significant digit or something like that. Okay, so it doesn't apply there. It doesn't apply to unit conversions. So saying like there's 1,000 meters in a kilometer, and I have 1 or 3 significant digits or whatever that is. Okay, it doesn't apply there. It doesn't apply to conversions. It doesn't apply to prices, actual prices. So if you've got something like it's offered for something like that, or what we call scalar operations. So just, no, there's only one P. Scalar operations, which would involve things like, double a number or triple a number, etc., etc., etc. So any of those things, does not apply. Okay, so let's say let's say we have this. What is the area of the square? Okay, so we want to say, and I purposely started off with this one, okay? So we want to say 8 times 8 is 64, so therefore the area is 64 millimeters square, right? This is what we want to say. Okay, but remember, you have to, if this is a measurement, okay, and we have 8 millimeters, then we only have one significant digit here. And we only have one significant digit here. So what I have to report is 6 times 10 to the 1 millimeters squared, or, I have to say, yeah. We only have one significant digit. Okay, and I want to justify this thing. Okay, so imagine having a ruler, okay, a centimeter ruler, and the ruler that we saw earlier had millimeter tick marks, but this one doesn't. Okay, so you've got this centimeter ruler, and it doesn't have millimeter tick marks, so you're looking at this, and so you're just eyeballing that this is 8 millimeters. Okay? And then you use the ruler to measure the vertical side. And also, remember that last digit that we have, we're just kind of eyeballing, right? So if this is, 1 centimeter, we're basically eyeballing that this is 0.8 centimeters on this side, and this is 0.8 centimeters on this side, or 8 millimeters and 8 millimeters. Okay? So if this is a measurement, okay, so if these are measurements, we have quote-unquote eyeballed the last digit. And in our case, it's the only digit that we have. And so we're eyeballing that this is 8 millimeters, and we're eyeballing that this is 8 millimeters because our ruler, whatever we're using, only has centimeter tick marks. Okay? Does that make sense? So we have centimeter tick marks, so we've eyeballed that this is 8 and that this is 8. And so we shouldn't say, just because we multiplied those together, that now we have 64 millimeters squared. Our answer should only have one digit of precision, so we're going to have to just say it's 60 millimeters squared, okay, or 6 times 10 to the 1 millimeters square. Huh? Is that all right? This is the part that it just feels uncomfortable and uneasy, okay? But you have to realize when you see something like this, if it only has one significant digit, that basically means you've just eyeballed that last one, okay? Because we're in the idea that, you know, you report the ones that you know, and then that last digit has been eyeballed. So if we did have, let me just copy everything here.
So it's really 64, but because of the rules, it's 60.
No, it's not 60. It's, well, we can't say that it's 64 because we don't know how long this thing is. Now, if somebody reported, okay, if this was not a measurement, and someone says, here, this is 8 millimeters and this is 8 millimeters, okay, and they're not measurements, then the answer is yes, the area of this square is 64 millimeters, if they're not measurements, okay? It's the difference between, do we know what we're dealing with, or did I measure this, which implies that that last digit is a guess, okay? So when we looked at those rulers, when we looked at those burettes and those things, we were trying to take measurements, okay? And we have a scale and we've got little tick marks, but then if we look closely, we see, you know, it's not exactly at any of those tick marks, so we have to guess that last digit. And because we're guessing that last digit, our answers have to take into account that that last digit contains uncertainty. So let's say we had another situation, and we have the little tick marks this time. So actually, yeah, let me just so this time, you know, I've got 1 centimeter, 0 centimeters, and I've got tick marks here. So this is 0.5 centimeters, and so on and so forth, and same thing over.
I have a question.
Yes.
How do you get those so evenly spaced? Are you running off the grid or something?
No, I'm not. They're not evenly spaced actually. They're.
They look pretty good.
Well, thank you. Yeah, I'm just. I have a tool to draw straight lines, but that's all I've got. Okay. So let's say, you know, I've got something over here, and we're going to draw a square, and this one, whoops. Let me just erase this 0. Put the numbers on the other side. One, 2, 3, 4, 5, 6, 7, 8. Okay. And so now I'm going to draw a square. Why is this not? Okay, so this not as accurate as I wish it were, but now we have to take a measurement. Okay, so we have millimeter tick marks on our ruler. Sorry. so we would report that the length of this side is now what? 8.0 millimeters. Okay. Or if you want to say using centimeters, you can say it's 0.080 centimeters. Either of those forms are okay. So this length is 8.0 millimeters, and then this side would also be 8.0 millimeters, okay? Because you're trying to eyeball where this last thing is, and it seems, okay, yeah. It goes out to the last tick mark, and my best guess for the next decimal place would also be 0.0. And so now, again, these are measurements. So what is the area of the square? So now we do 8.0 millimeters times 8.0 millimeters. And we would get 64 millimeters square. Okay? And this has two significant digits. We have two significant digits there. We have two significant digits here. So our answer can have two significant digits. Because your final answer, whatever it is, cannot have more significant digits than the measurement with the fewest significant digits. These are tiny little squares, right? 8.8 centimeters. Does this feel okay? All right, let's say you have if you have 6 of these squares, what is the total area? So if you have 6 of these squares, what's the total area of these 6 squares? Using the proper significant digits. Okay, so with 6 squares, we would do 6 times 64. And what do I get? Let me just 6 times 64. I get 384, right? 384 millimeters squared. What's that?
I don't know, because I got something else because I was going to pull my head. I just
Okay. But our answer can only have 2 decimals, or 2 significant digits, right? So we have to report 380 millimeters squared, which might be ambiguous, so we might say 3.8 times 10 to the 2 millimeters squared. It feels so terrible, I know. Yeah, okay, so the 64 millimeters squared is the result of measurements, okay? The 6 is a count, okay? So that doesn't go into play, because if the 6 were a measurement, then we would, our final answer would only have 1 significant digit, okay? Yeah. So here, this is what we report. I know, it feels terrible. So we'll try some practice here, okay? Okay, so we'll do some practice problems. Okay, so I'm going to put numbers here. If the number is followed by a unit, assume it's a measurement. Okay, so if the number has a unit, it is a measurement. Okay, if there is no unit, it is a count. It is a count, or just not. It's not a measurement. Okay, so do the calculations and report with the proper significant digits. Okay.
Hey Miles, could we take a break now?
Okay. Here. Okay. We'll do the problem. I'll put the problems up on the board, and then we can take a break. You can come after the break, finish the problems, and then we'll go over the answers. How's that? Okay, so yeah, we'll go ahead and we'll take our break now. And then you guys, after the break, you can come back, work on these problems, and then we'll go over the answers.